Chi-square test for goodness of fit. Hi everyone, my name's Manuel Espinosa. I'm a master in mathematics, and the target of this video is to perform the 4 steps process for a chi-square test for goodness of fit. You use the chi-square goodness of fit test when you have one categorical variable and want to determine if your sample data matches an expected or theoretical population distribution. One categorical or qualitative variable, and the variable is discrete. So let's see the application in this real-world problem. Imagine that you are the quality assurance manager at a company that manufactures a popular candy brand, Choco Bottoms. The marketing team boldly claims on every bag that the color distribution of the candies is uniformly distributed for all the colors: red, blue, green, yellow, and orange. Lately, you've been getting social media complaints from customers claiming that they are getting rip-off on blue candies. You decide to pull a massive random sample of 500 candies from the assembly line to test if the company's distribution claim is true. When you dump out and count your sample of 500 candies, here is what you observe versus what you expect to see based on the 20% claim. You need to determine if the differences between what you saw, observed, and what you expected are just due to minor random chance, or if the factory machines are genuinely miscalibrated. State: chi-square test for goodness of fit. Null hypothesis: the proportion of red, the proportion of blue, the proportion of green, proportion of yellow, proportion of orange are all the same, 0.20 or 20%. Alternative hypothesis: the proportion of blue color differs from 0.20 and any other color proportion is different than 0.20 as well. Another way, so we can say that the null hypothesis is the distribution of candies color is uniform, and the alternative, the distribution of candy colors is not uniform. And the alternative hypothesis is going to be the claim. Since the significant level is not stated in the problem, so we are assuming that the significant level that we are going to use is 0.05 or 5%. To calculate the expected counts, we are going to multiply the sample size of 500 candies by the individual proportions. Step number 2, plan. Checking the random conditions. So we have a random sample of 500 candies. Large counts. All the expected values are at least 5. 100 is greater than 5. So that means that all the conditions are met. Step number 2, do the calculations. Find the degrees of freedom. Degrees of freedom equals the number of categories minus 1. There are 5 candies colors. Minus 1 equals 4. Degrees of freedom is 4. Calculate the chi-square test statistic. That is the difference between the observed counts and expected squared compared to the expected at the null. Example: 115 minus 100, the difference squared divided by 100, plus the difference of 70 and 100 squared over 100, plus the difference of 105 and 100 squared divided by 100, plus the difference of 120 and 100 squared divided by 100, plus the difference of 90 and 100 squared divided by 100. Chi-square test statistic is 2.25 plus 9 plus 25 plus 4 plus 1 equals 16.50. By using the table of the chi-square distribution, the intersection between a degrees of freedom of 4 and a significant level of 0.05 give me a critical value of 9.488. The chi-square critical is 9.488. The chi-square distribution is a family of curves that depends on the degrees of freedom, differs on the degrees of freedom, are skew right, and all the x values are positive. So we have a critical value of 9.488. So that critical value divides the graph into two sections. On the left side of 9.488, so we have the fail to reject area. And on the right side, we have the rejection area or rejection region. A chi-square value of 16.50 is on the right side of the critical value, so it falls in the rejection region. So then we can reject the null hypothesis. By calculating the p-value, so the p-value is in the first row, so the p-value decreases from left to right, so a chi-square of 16.50 is in between 14.860 and 16.924, So our p-value is going to be in between 0.002 and 0.005. So any value in this interval is less than the significant level alpha of 0.05. So since the p-value is less than alpha, so we are going to reject the null hypothesis. By calculating the p-value, so the p-value is in the first row, so the p-value decreases from left to right, so a chi-square of 16.50 is in between 14.860 and 16.924, so our p-value is going to be in between 0.002 and 0.005. So any value in this interval is less than the significant level alpha of 0.05. So since the p-value is less than alpha, so we are going to reject the null hypothesis. By using the graphing calculator, so we get an exact p-value of 0.0024 and 0.0024 is less than 0.05, so the p-value is less than the significant level. Step number 4, conclusion. At a significant level alpha of 0.05, there is enough evidence to support the customer's claim that the distribution of candy colors is not uniform. In other words, the customers are right. You have statistically significant evidence that the candy distribution is not uniform 20% each. As the quality assurance manager, your next step is to halt the packaging line and recalibrate the sorting machines, specifically investigating why the system is underproducing blue candies. Thank you for your attention. Thank you for visiting my channel.